Hi everybody, coming back now for week 14, looking at chi-squared tests. So two types of tests we're gonna look at: goodness of fit tests. This is just where we're given a proposed distribution of data, then we're looking at the actual observed data and comparing to see if they fit, if there's a good fit between them. And then contingency tables. So goodness of fit, of course, is one-way frequency table. And we're only measuring one quality about each item in our sample. Contingency tables are sometimes referred to as two-way tables, because we are measuring two different values about each item in our sample. Similar to our correlation regression in the last unit, where we're measuring two numerical variables about every item in our sample. Here we're going to be measuring two categorical variables. And in the contingency tables, there are actually two types of tests. There are tests for independence. Helps if I can spell. Let me try that again. There we go. And then there's tests for homogeneity. And they're really the same test. Test for independence is just saying the two variables being measured don't have an effect on each other, or they do have an effect on each other. Homogeneity is just saying the proportion of occurrence in all the horizontal categories is the same for each vertical column. So the distribution, the probability distribution being used here is the chi-squared distribution. So that symbol that looks like a scripted X is the Greek letter chi. It's spelled C-H-I, but it is pronounced chi. And of course, the 2 means it's squared. And we'll look at that distribution as we go on. But one thing to note, that it is not a bell curve. It is always skewed to the right, like that. And because similar to our t-distribution, it depends on degrees of freedom, so the size of the sample makes a difference. And the chi-squared distribution and all of our chi-squared tests are always going to be right-tailed tests. So what we're going to be looking up is what is the alpha is going to be that area in the right tail always. So for goodness of fit, what we're looking at is we're given some proposed frequency, whether there's equal frequencies or some proportions, percents or whatever. And we're going to form a single row or a single column of frequency table with that data. And we're going to test to see if the observed frequencies, the distribution, fits the claimed frequencies or the proposed frequencies. An example of this is M&Ms. M&Ms used to claim that in their package of regular M&Ms, 30% were red, 20% yellow, 20% green, and 20% orange, and then 10% were brown. So you could gather up M&Ms and count how many of the M&Ms are red, yellow, green, orange, or brown, and compare them to those proposed percents. And we'll look at that process as we go through our examples here in this unit. So to conduct a goodness of fit test, the first hypothesis is going to be that they fit the proposed percentages. The alternative is going to be that there's at least one of them is different. But we're looking at these frequencies, and we have to make sure they agree with either a uniform, which means all of them are the same, or maybe a normal distribution or some other proposed distribution of that data. Like with the M&Ms, it was the percentages proposed for each color. Some symbols that we're going to use: O is going to stand for the observed frequency for each category. So if we're looking at the M&Ms, we count up. It's exactly how many red M&Ms do we actually have in our sample. E is the expected frequency. So we said we expect 30% to be red because that's what M&Ms is claiming. So we take our total, find 30% of the total. That's the number we would expect to have of red M&Ms in that sample. K is the number of different categories. So here we had 5 different colors. K would equal 5. There's 5 different categories. N is the total number of trials. So that would be the total number of M&Ms that we had that we counted up for the colors. And P is going to represent the probability of each sample, each item falling within a different category. So, the probability if we select a random M&M, 0.3 or 30% is going to be the probability that's red. 0.2 or 20% probability that's red is yellow. So those are p-value, p or probability for each different category, for each color. So testing for goodness of fit, we have some requirements, just like all our other tests. As any of our tests, the data has to be randomly selected, so it has to be simple random samples from the population. It must consist of the correct type of data. They must be frequency counts from the categories that we're looking at, that we're analyzing. And then, similar to the binomial test, the test for proportions, where we had to be able to reasonably expect at least 10 successes and 10 failures. Here, each category must reasonably be expected to have at least a frequency of 5 in each of those categories. So for the M&Ms, 10% for brown was the lowest percent. We would have to have a sample size of at least 50, because 50 times 10 would be 5. We have to reasonably expect to have at least 5 of every category. So that would give us 5 of the brown M&Ms. Next, we have our hypotheses. The null hypothesis is always going to be that the frequencies agree with the claimed distribution, whether they're the same or some proposed percents. And the alternative is going to be that at least one of the frequencies is different than what is proposed, or simply to say that the frequencies do not agree with the claimed distribution. The test statistic then is going to involve, again, this is just the symbol chi-squared. That's our test statistic. The observed frequencies minus the expected frequencies. Then we're going to square that difference. And then we're going to divide that by the expected frequency for each category. Notice we have this summation symbol here. So like for M&Ms, there's 5 different colors. We would calculate this for each of the 5 colors and then add the 5 of them together to get the total chi-squared statistic, the test statistic. Now we could do the p-values with technology, which is easier, or we could use the table found in the textbook. So let's pull up that table quick so we'll have it here. So if we're looking at course home here, we're going to go to eText, go down to Appendix A is where all our probability tables are. We'll open up the tables. And we need to get to table A4, it said was the chi-squared table. Internet's running a little bit slow today. Sorry about that. There we go. So the first one is binomial table. Second one is normal. Third one's next. Also going to be normal distribution. Then we have T distribution. Here's the chi-squared table. So this is the table that's going to allow us to find our critical values and to estimate our p-value. Notice we have degrees of freedom down the left side, and on top we have different p-values. Remember, these are always the right tail. We're not going to be able to get an exact p-value. We're just going to be able to take whatever degrees of freedom we have. Let's say we have 9 degrees of freedom, and we look at where it was our test statistic between 16.9 and 19.0. All that's going to tell us is that our p-value is between 0.025 and 0.05. We can't get the exact p-value, but we can tell you whereabouts it is in the range of numbers. So we can find an exact critical value here. K minus 1 is our degrees of freedom. So we could look up K and we could look up whatever alpha value we're using. Alpha, of course, is that right-tailed area in the distribution. And it would give us an exact critical value. So again, let's go back to 9 degrees of freedom here. If we're using alpha of 0.05 up here, that would intersect right here. 16.919 would be our critical value. And for our chi-squared test, our rejection rule is always going to be if the critical value is greater, or if the test statistic is greater than the critical value, we will reject. Or if the p-value is less than alpha, we will reject the null hypothesis. So to construct this good test, we need to find the expected frequencies. If they're equal, we just take the total sample size divided by the number of categories to get the expected frequency for each category. If they're unequal, then we have to use whatever distribution is given. Usually it's a probability. For the M&Ms, we were given 30%, 20%, 10%. So convert that to a p. So 30% would be 0.3. And then do n times 0.3. Whatever n is our sample size times 0.3 will give us the expected number of red M&Ms in that sample. And we do that right down the line for all the different categories. So filling in the expected frequencies here. So a single die is rolled 45 times, and the following results of the die are recorded in this table. We would expect that each number on the die would be equally likely to occur. So in 45 rolls, we take 45 divided by 6 different numbers on the die. We would expect each of those expected frequencies to be 7.5. So we'd fill that in all the way across that bottom row. If they're not equally likely, we have to be given a probability. So here in this table, this is a loaded die. We're given percents here that we expect them to come out. It is loaded so that 1 will come up half the time, or 0.5, and all the other numbers will come up only 0.1 of the time. So to get this number down here, we take 45 times the probability. So for 1, that's 0.5, so 45 times 0.5 gives us 22.5. For the others, it's 45 times 0.1, which is 4.5. That's where we got the 4.5 as these expected probabilities. And then we generate the test statistic. We take the observed value minus the expected value. We square that difference and then divide by the expected value to generate the test statistic contribution for each value here. So like we said, the 1 will have a contribution to this test statistic, the 2, the 3, the 4, the 5, the 6. So we're going to have 6 of these calculations, 1 for each number, and then we're going to add them all over to get our total test statistic. So just a little bit of a graphic. This one's a little bit simplistic, but it's just saying if the observed values and the expected values are close to the same, we're going to have a large p-value and a small value of chi-squared, a small test statistic, which means we're most likely going to fail to reject. If the expected and the observed values are far apart, then we're going to have a large test statistic and a small p-value, and we're most likely going to end up rejecting it. So if we fail to reject, we're saying that the observed values are a good fit with the expected distribution. If we reject the null hypothesis, we're saying that the observed values are not a good fit with the assumed distribution. So an example we're going to look at here is we're going to look at measured versus reported. A lot of times people report data saying, this is the weights of patients or whatever. How do we know if that data is actually measured? Did we put those patients on a scale, or did we just ask them what they weighed? So we saw this in one of our hypothesis tests where we were looking at the reported weight versus what they actually weighed to test to see if there was a significant difference. And we found that there kind of was. Most people underreported their weight. Well, another phenomenon is if you actually look at real weights of people, the last digit. So like if we were 121 or 171, those both end in ones. The last digit is 1. Or 153 versus 213, those both end in 3s. They would be categorized as the last digit of 3. And if you actually weigh real people and put them on a scale and get their actual weight, that last digit occurs with equal frequency. It's what they call a uniform distribution. Every last digit occurs the same amount of times if you're actually weighing people. So we're going to take a table here of people's weights, and we're just going to categorize their weights by the last digit. Now we find here that 1,175 of those weights ended in a 0. All the other weights are much, much smaller than that, except for the 5 is 731. Just by looking at this, I can tell you that most likely these were not actual measured weights. These were asking the patient how much they weighed. Because if you're asked how much you weighed, you're not going to say 162 pounds, you're going to say 160 pounds. Or 165 pounds. The chances of reporting a 0 or a 1 are greatly increased when you're just having the patient report their weight. But if you were to put them on a scale, any of these digits would be very likely to occur as the last digit of the weight. So I'm saying this is most likely, before we even perform the test, probably these weights were reported rather than actually measured. So to do the test, let's test to see if these fit with being measured weights. If you remember, if they were measured weights, each of these digits, the last digit of the numbers, would occur with equal frequency. So let's test to see if there's a significant difference between these observed frequencies and what we would expect if these were measured weights. So we need to check our requirements. First, the data is randomly selected from our subjects. Second, the data does consist of frequency counts, so we can see it in the table. And second, if there's 2,784 and there's only 10 digits, the expected frequency of each is 2,784 divided by 10, or 278.4, which is definitely larger than 5. So we definitely expect more than 5 frequency for each category. So all of our requirements are met. We can go ahead and proceed with the chi-squared test. So our original claim is that they do not fit these frequencies. The proportions are not equal. If that is not true, the alternative would be that they are all approximately equal. Now, remember we said this is what we end up making the null hypothesis, is that they are all equal. So the null hypothesis, the claims or the proportions of each last digit are about the same or close enough to the same. The alternative is at least one of them is different than what we would expect. So then our step 4, we're going to test this at the level of significance of alpha of 0.05. Since there wasn't one given, remember we said we usually take alpha of 0.05 to be our level of significance. So because we're testing this claim about a distribution of the last digits, this does fit a goodness of fit test, so we are able to use the chi-squared distribution. So let's look at, these are observed values. We need to now go through and calculate the expected values. That's going to be just the total number divided by 10, because there's 10 digits. So that gives us that 274.8 that we saw earlier. And we do a table. So we put our observed values in here. We're going to do observed minus expected. Then we're going to square that. Then we're going to divide by the observed. I actually have this data put into Excel, so I'm going to do this for you. So this is the expected value. These are the observed values. I just did a sum here to prove that it does add up to 2,784. So this is going to be my observed minus expected. So this minus, oops, come on. Equals this minus that. So that's my observed minus expected. Then I'm going to square that. And then I'm going to do that value divided by the expected value, this one again. So notice for the leading digit being 0, we get a contribution to our test statistic of 2,887. Already that's a pretty large contribution. So we're going to do this for each of the data points. Now notice that the smallest one here looks like it's the 8. 8 is actually the closest to being expected value because it's the smallest contribution to our test statistic. So now we're going to add these all up to get a sum. We get 4,490.174. That is our chi-squared test statistic. which is what we calculated right here, 4,490.174. Is that significant? Well, there are 10 categories, 10 last digits here, 0 through 9. So if we go to our table here, 9 is our degrees of freedom, 10 minus 1. Alpha of 0.05, so that is 16.919 is our critical value of our test statistic. So what that's saying is if the test statistic is greater than 16.919, we would reject HO, that null hypothesis. Well, we're definitely 4,900 or 4,490 is definitely bigger than 16.919. So we definitely reject that null hypothesis. Well, what if we wanted a p-value? You can see here, this is our reading from ExcelStat. It gives us the critical value, the actual test statistic, and it gives us the p-value. Of course, it also lists the alpha value in there. We can find the p-value in Excel without ExcelStat by simply doing a chi-squared distribution. So right here is chi-squared distribution. X is this value. My degrees of freedom are 9. And true, this is cumulative. So now this is giving us the left tail area. We want to do 1 minus that to get the right tail area. I don't know why Excel gives the left tail area, because when it's chi-squared distribution, it's always the right tail that we're interested in. But you can see we get 0 is that probability. We got a p-value of basically 0. They were saying 0.0001. It's actually a little bit smaller than that. But you can see why Excel would give 0. There is also a chi-squared function in here. You can see we have a chi-squared test right here. So if I click on FX here, it's going to ask me my actual range. So this is my actual data right here. These are the actual frequencies. The expected frequencies, I'm going to click on these right here. Now, Excel now knows that there are 10 items in each list, so it knows from this that there are 9 degrees of freedom. So what it's going to give us back is the p-value of this. Notice that's 0. So Excel is telling us that the p-value here is 0. If I go to ExcelStat, or not ExcelStat, StatCrunch, I should say. Here I have the same data in here. Now I did not put in the expected value, but I don't have to. So I'm going to go down here to goodness of fit, and there are other goodness of fit tests. I'm only doing the chi-squared test here. My observed frequencies are in variable 2. Now I could put in my expected frequencies in one of these columns, but these I'm expecting them all to be equal, so I'm just going to click this box. All cells should be equal, so all the categories should be equal proportions. And that's all I really need to do. So I'm going to just hit compute. Now here I did have expected highlighted down there, so it did give me the expected value for each of those observed values, but it's giving me my chi-squared test statistic, the 4,490.1739. And again, it is telling me my p-value is less than 0.0001. We found that actually returns to be basically 0. It's too small it rounds to 0 in our technology when we do it in Excel. So that's where this display comes from. We don't need the ExcelStat add-in to do those calculations in Excel. So this is that curve that I demonstrated earlier. It's always skewed to the right, to the upper tail. The critical value we found was 16.919, and our test statistic, 4,490, is way out there. So we're definitely in the rejection region. So we reject the idea that those proportions are all equal. And so we go, the alternative is that they're not equal, or at least one of them is different. So there's significant evidence here to support the claim that the last digits do not occur with the same relative frequency. What that means is, as we mentioned earlier, is that tells us that this data was probably not actually measured. It was just self-reported by the patient. Telling us to question its reliability a little bit. So you can see here, we took a data set where we didn't know, we just had the numbers here, the frequencies, and we were able to make conclusions about how the data was gathered just by knowing what the distribution should look like. So this goodness of fit test, as I said, indicates that subjects probably reported their weight rather than being actually weighed. The second example is an important example. We're talking about Benford's law, and it actually was discovered first by someone named Simon Newcomb. Some textbooks refer to it as the Newcomb-Benford's law. What it's about data sets that are legitimate data sets or data sets that are fraudulent. And what both Newcomb and Benford discovered is in legitimate data sets, the leading digit is more likely to be a smaller number. In fact, 1/3 of the time, the first digit, when you're talking, especially in financial situations, and almost 1/3 of the time, the first digit in the number is a 1. And only like 5% of the time is that first digit a 9. You can actually see that down here in this table, where this is the leading digit in the number. Now, the leading digit's never going to be a 0, because if it's a 0, we'd just leave it off, and the next digit would be the leading digit. And you can see what Benford's law says is that 30.1% of the time it's a 1, 17.6% it's a 2, all the way down to 5.1% it's an 8, 4.6% of the time it's a 9. When people make up numbers, they tend to not pay attention to this. They tend to just make up random numbers, and they get more of an even or uniform distribution. So this is used by the IRS for fraud detection. If people are making up numbers on their reported incomes and expenses and stuff like that, it's used by other companies as well to detect fraud coming. Internet companies here use it to predict cyber attacks. If data is being altered through some sort of a virus or other cyber attack. So let's check the requirements here to perform this test. The data is a random sample from a larger population. The data does consist of frequencies in each category, and each frequency is expected to be at least 5. So 271 items in our sample. The smallest percentage was the 9, which is 4.6%. So 271 times 0.046, which is the decimal form of 4.6%, gives us an expected frequency of 12.466, which is bigger than 5. So that means all of our requirements are met here. So step 1, we make our claims. The null hypothesis is going to be that P1 is 0.301, P2 is 0.176. Again, that just comes from these percents given here. The alternative is going to be that at least one of them is different from that. And so if the original claim is false, then at least one of those proportions has to be different than what is claimed there. So this is the actual hypotheses written out. Null hypothesis is that's what those proportions are going to be. The alternative is that at least one of them is not equal to what is given there. Again, there's no level of significance specified, so we're going to use alpha of 0.05. So now we calculate our expected value for each. We take the 271, which is the total frequency, times that percent, the 30.1% becomes 0.301. Gives us an expected value of 81.57. For 2, the percent was 17.6%, gives an expected value of 47.6960. And so we do the observed minus expected, we square it, and then we divide by the expected to get our contribution to the test statistic. I'm going to go into Excel. I've got this data set entered as well. These are the observed values. These are the percents. Let's calculate the expected values here. This is going to be the 271, which is our total, times this value, the 81.571. And we're going to do that for each of them. And so then now this will be our observed minus expected. So this is going to equal the observed minus the expected. This, we're going to square that. And then here we're going to divide that number by the expected again. So now here we get very small numbers. Let's do that for each of them now. So here's our observed minus expected, squared, and then divided by the expected. Let's get the sum here. That adds up to 11.279. Well, what is going to be the critical value? Well, we're only going 1 through 9 here, so K is only 9 categories. So that means we only have 8 degrees of freedom. So we'd be looking up here now. Still 0.05, so we get 15.507 is our critical value. So that means if we have a test statistic of greater than 15.507, right here is what we have, we would reject. Well, we saw here we got 11.279, which is also what they have listed here. That is not greater than 15.571, so we would fail to reject the null hypothesis here. This is the ExcelStat output. If you wanted to use that, the p-value of 0.186, I can find that p-value in Excel without using ExcelStat. So this is just going to equal 1 minus the chi-squared distribution right here. 11.279, comma, 8 degrees of freedom, and true for cumulative. There is 0.186. There it is, 0.186 is what they gave here. Or we could use just the chi-squared test right there. So I'm just going to click here to open up the window. Here's my actual values. Here's my expected values. And there, 0.186 is my p-value. So you can see that chi-squared test function gives us the p-value right off. Exactly what we would have got if you used ExcelStat. We could do the same in StatCrunch. Let me go there. I don't have these values entered, so let me get them entered here. I'm just going to copy them right out of here. So I'm going to use my observed. Shut this window down. My observed and my expected values. I don't need my percents in here. And let's do the goodness of fit, chi-squared. Observed column is V4. Yep, and the expected is V5. So we hit compute. And there we go. There's our test statistic, 11.279, and our p-value of 0.186. So exactly what we got from our other methods. So we failed to reject. There's not sufficient evidence to reject the null hypothesis here. So that means there's not sufficient evidence to claim that these digits do not follow the expected distribution set out by Benford's law. So that means this looks like it's a legitimate data set. We would say that these numbers do not appear to be fraudulent. They appear to be actual naturally occurring numbers. Now, one thing we can do to confirm this is we can graph it. So this is the graph of the percents in green here, the percents that are set out by Benford's law. You can see it makes a nice little exponential curve, negative exponential curve. The red dots then are the percentage if you converted them into a proportion divided by the total for our observed data points. You can see they follow, I mean, they're not perfect, but they follow that expected green curve fairly well. So it confirms that, yeah, this data set appears to fit what is proposed in Benford's law. So those are goodness of fit tests. Really all we're looking at is one variable for our set of data and with multiple categories. If it's only 2 categories, of course, we could just use a test for proportions. So this has to be more than 2 categories, and we can perform this test using that chi-squared distribution. Next section, we're going to look at what happens if there's 2 variables. We're looking at a two-way frequency table or a contingency table, and to perform chi-squared tests on that data.